Welcome to Brain Vision.
A stoppered test tube traps 25 centimeters cubed of air at a pressure of 1 atmosphere and a temperature of 18 degrees Celsius. The cylindrically shaped stopper at the test tube's mouth has a diameter of 1.5 centimeters and will pop off the test tube if a net upward force of 10 newtons is applied to it. To what temperature would one have to heat the trapped air in order to pop off the stopper, assuming the air surrounding the test tube is always at a pressure of 1 atmosphere? Okay, so we are going to start from the gas law, ideal gas law. So pressure times volume is equal to nRT. And from that, we can say that if we are dealing with two scenarios of ideal gas, pressure 1 over pressure 2 dot volume 1 over volume 2 is equal to, so copying these for one gas and another gas and then dividing through the equations, as demonstrated on a previous video, is equal to T1 over T2. And we're going to call this equation 1, and we're going to start a new whiteboard. Okay, so from P1 over P2, we're just going to write this out again, dotted with, so multiplied by V1 over V2 is equal to T1 over T2. And given that the volume of the test tube before it pops off is going to be the same, we can cancel through by this amount here. So we just have P1 over P2 is equal to T1 over T2. And the unknown quantity is the temperature of the second gas. So we're given a starting scenario, we have a finishing scenario, we know the pressure and temperature of the starting scenario, but we can calculate the pressure of the end scenario because we know what force is required to pop the stopper off. But what we don't know and what we're required to find out is at what temperature does this occur. So rearranging this to make our unknown the subject of the equation, we have T2 is equal to P2 times by T1 divided by P1. And so we know, let's write out our known so far. So pressure 1 is at 1 atmosphere, which is equal to 1.013 times 10 to the 5 pascals. And T1 is equal to 18 degrees Celsius, but we're doing an ideal gas calculation, so we need to write this all in Kelvin. So it's 273 plus 18 to convert from Celsius to Kelvin, plus 18, which is equal to 291. And so temperature is equal to 291 Kelvin, degrees Kelvin. And actually, let's just get rid of the degrees because it's slightly confusing. 291 Kelvin. And we can calculate our second our pressure that we require to exert 10 newtons of force. So pressure is equal to force divided by area. And the force that we have is 10 newtons, and the area is just pi r squared, but we need to convert that to meters, so we're working in standard SI units, so standard international units. So this is equal to 10 for 10 newtons divided by pi times 1.5 divided by 2, because 1.5 is the diameter, times 10 to the minus 2, so we're in meters as opposed to centimeters, squared. And it turns out, and also we have to add on the 1 atmosphere, so 1.013 3 times 10 to the 5, because what we're looking for is a relative force, and the outside is already at 1 atmosphere. So the relative force that we require is 1 atmosphere plus this amount here. So it's important to remember that you're not, if it was in a vacuum, you'd just take this bit off, but we're not in a vacuum. We're at standard atmosphere. We're at a standard temperature and pressure, or no, we're not, sorry. We're at standard pressure, but we're at 18 degrees Celsius. So we need to add on this additional 1 atmosphere here. And it turns out that this, after putting this on a calculator, is equal to 1.578 times 10 to the 5. And now we have 3 numbers to put into our equation up here. So let's just call this equation, it doesn't really matter, equation 4. So we put these 3 numbers, so P1, T1, P2, into this equation up here. And it turns out that T2 is equal to 454 Kelvin. And the answer that they're looking for is to put it in degrees Celsius. So this is the 3 significant figures as well. So this is equal to 181 degrees Celsius. But just by subtracting off 273 of this number, we get to 181 Celsius.